All right, on to what I'll consider the bad news. Right, so remember, the good news is that because of all the things we're doing as a nation and as a world, we have affected the growth factor of this disease. And while things are still serious, a lot of people have been affected negatively in multiple ways. Um, we've banded together and we've made a difference. So that is positive. But there is this other issue, the herd immunity threshold. And the things we're going to talk about are based on mathematical models. And so they are to be taken with a grain of salt, but not too much more than a grain or two. And so this will end up being troubling. It will relate to the question of, well, what do we do now? It seems like we're making a difference. Things are not as bad as they could be with COVID-19. So I suppose perhaps it's time to get back on with things. Perhaps. So, we have around 500,000 confirmed cases. Of course, it was higher this morning. I made this slide a day or two ago. Um, but there are some issues with that number. We're doing limited testing, running out of supplies, though that may change. I did hear that Fauci was talking about a test that would be widely available shortly. That's important. And it seems as though 20% at a minimum, if not 50% of COVID-19 cases are either asymptomatic or so mild that folks wouldn't really notice it, um, which is good. Those are people that are presumably not dying or clogging up the ICUs and whatnot. But the point is that maybe at best we have actually a million or a couple million cases, whereas we've recorded 500,000. Now, how does this affect our decision to go back to business as normal? Well, it turns out that's not very many people in the scheme of things. And the concern, and so I'm not original in talking about this, is that if we all just go back to work and school, then those curves that we saw that were flattening out will become steeper again. And this is related to this idea of a herd immunity threshold. So when studying disease outbreaks, we've seen there are a bunch of mathematical models like SI and SIS and SIR and so on. And R naught is an important part of those models. It's a ratio of various parameters. And recall that outbreaks, epidemics occur when R naught is greater than 1. It's indicating that it's spreading at a certain, if the growth factor is greater than 1, then you're getting exponential growth. That's not good. Now, I'm sure you've heard of the fact that there's multiple researchers working on vaccines. Of course, that's going to take a while, which is good in many ways. We don't want a crappy vaccine out there that has worse side effects than the disease it's trying to fight. Um, the importance of a vaccine isn't just to prevent contracting the disease, but also to prevent the spread of the disease. And this is where this herd immunity is going to come in. All the models that we've talked about so far assume a population that's entirely susceptible to a disease. And so we're going to turn that on its head a little bit. Part of the point of the flu vaccine every year is not so much for, say, a healthy person like myself with a robust immune system to avoid getting sick for a week or so. It's to avoid me spreading it to a bunch of other people that may have more severe consequences. So this is a little like social distancing. It's not that uh, I need to stay home because I'm afraid of dying of COVID-19. Seems pretty unlikely. It's that I'm staying home so that I'm not spreading it to other people who might suffer consequences. And again, I might also suffer consequences, of course, but it's multiple. So the herd immunity threshold is a number that characterizes how much of the population needs to be immune in order to prevent an epidemic. You can think about this like measles, rubella, catchy diseases that we're all vaccinated against. So you can't really have a nationwide measles outbreak, but we do see little outbreaks of things like whooping cough and whatever because of anti-vaxxers, and which can create communities of susceptible individuals, which can then become infected, which can then transmit the disease to folks with compromised immune systems, like folks on chemotherapy or whatnot, and they can get sick and get hurt. So the idea is if enough people are immune to something, say like measles, then you're not worried about an outbreak because you can't, like I can't catch measles. I'm vaccinated against it. So if somebody had measles and I was in contact with them, they can't pass it on to me, and then I can't pass it on to somebody else. So we're gonna think about this in terms of some diagrams. And HIT, that's herd immunity threshold. That's the acronym I'll use. Imagine we have an R naught of 3. Remember, R naught is the sort of the average number of people that an affected person transmits the disease to during the course of the infection. So this means that a given contagious person will, on average, infect 3 people. So we'll consider this with a picture. So we start with one infected person over here, and we imagine that they infect 3 other people. That'd be an R naught of 3. And those 3 people affect 3 other people each, right? So we go from one infected person to 4. This is that total cases business, total confirmed cases. So 1 plus 3 is 4. 1 plus 3 plus 9 is 13. And then we go to, say, a total of 27 more, so 40. So this is exponential growth, right? One person affects 3 people, infect 9 people, infect 27 people. Now, it's thought that COVID-19 is probably has an R value less than 3, but some estimates have been around 3. So how do we prevent this? Well, this is a worst case scenario. Remember that R naught is based on a well-mixed population of people that have not been exposed to the disease, completely susceptible. So how many people would need immunity to stop this outbreak? So first, let's imagine these first 3 people. What if 2 of them were immune to this condition? Well, if these 2 people were immune, none of the people they would have infected would become infected. We're assuming, right? So if all these grayed out spots were folks that were affected because of these 2 dots, they are no longer going to become affected. That's quite a difference. Now imagine that 2 out of these 3 were immune. Well, that would mean that these 6 people over here would not become infected. So what I'm suggesting here is that if 2/3 of the people had immunity, this would reduce transmission to 1. One person infects one person, infects one person, infects one person. Because there's so much immunity, it prevents exponential growth. We're increasing linearly. 1 person, 2 people, 3 people, 4 people. Let's do another example. So here's an R naught of 2, meaning that on average, 1 infected person infects 2 others. So 1 infects 2, the 2 infect 4, the 4 infect 8. Again, this is exponential growth. Think about how much of this population would need to be immune to prevent this sort of growth. Half, right? If 1 out of the 2 first people, and 1 out of 2 of the second, and 1 out of 2 over here, you would reduce this to 1 to 1 to 1. Now, I'm not saying this is the best case scenario. More immunity is even better. But this is the threshold, the herd immunity threshold. What's the minimum number you need to prevent exponential growth, to prevent R naught from being greater than 1, which is how we define mathematically an epidemic. So here's the formula. It's not very hard. The herd immunity threshold is related to R naught by this. It's 1 minus 1 over R naught. So for example, we did an example with R naught is 3. So then the herd immunity threshold is 1 minus a third, 2/3. And that makes sense with our pictures. And then if R0 is 2, that was the previous example, then the herd immunity threshold would be 1 minus a half, which is half, which also checks out. So last week we looked at a possible value for R0 for COVID-19. And again, R0 is, technically it's the number at the beginning of the epidemic, assuming no countermeasures and a completely susceptible population. So technically R0 doesn't change. There's another thing called effective R that changes over the course of the epidemic. But we'll be a little careless here. In any case, 2.28 was one possible value. And this would mean we would need a herd immunity rate, not immunity rate, threshold, sorry, this should be a threshold. I'm going to pause that, fix that. There, herd immunity threshold of 1 minus 1 divided by 2.28, which is 0.56, or around half of the population. Consider, and we'll get back to the number in a minute, the seasonal flu, for example, has an R0 around 1.3. And so a herd immunity threshold would be 1 minus 1 divided by 1.3, which is about 0.23. And I couldn't find the numbers for this flu season, but the previous flu season, the estimates for the number of people vaccinated from the flu were well over 23%. So, and I hadn't realized this before. This is something that I recently learned. I had very seldom got the flu shot because I'm not overly worried about the flu. I got it a couple of years because I had young children and I didn't want to pass it on to them. But now I recognize that part of the point of getting a flu vaccine is not for any inconvenience that I might experience, but if I have a flu vaccine, then I'm less likely to transmit the flu to, say, students or faculty or grocery store workers or anybody who might have a compromised immune system or underlying conditions that make the flu a more serious problem for them. And so I can safely tell you that having learned about this, because we're in a pandemic, it's the sort of thing that I plan on getting more regularly now. Again, not because I'm worried about the flu myself, but because I realize that I can be part of the solution during flu season for other people. And so this would be part of the reason that we might get vaccinated for COVID-19. Even if you're a super healthy young person, why get vaccinated? Well, to prevent the spread. So let's go back up to the top of this slide where I calculate the herd immunity threshold for COVID-19 of 0.56. So 0.56 of the American population, that's about 160 million people. And at best, we've had a couple million cases. So we're nowhere near the immunity threshold. Meaning, if we all started going back to work tomorrow, it would spread, and it would once again overwhelm ICUs and all these kinds of things. So I'm sure you're reading about various things being kicked around in terms of testing and whatever, but it's going to be tricky reopening the economy and trying to expose people maybe carefully to gain more immunity or waiting for a vaccine to be fast-tracked. Yeah, so here's another example. So R0 for measles, this from last week, ranged between 12 and 18. And how can it range? And it depends on, again, the society that you're working in. Is it close proximity living? Is it rural? What sort of social distancing are you doing? So R0 can vary depending on the community that it hits. So taking the lower end of R0, 12 for measles, the herd immunity threshold is 92%, right? But we all get vaccinated for the measles. Thus, we don't have measles outbreaks for the most part. So this is the idea. widespread vaccination prevents epidemics. This is part of the problem to COVID-19, is that none of us had been exposed to COVID-19 prior to this outbreak. Say versus the seasonal flu, which it was often compared against, lots of us have experienced the flu. And while that doesn't protect us necessarily, it reduces, on average, the effects of the flu. And because there's varying degrees of immunity in the population, it slows the spread of the flu. And the flu is less lethal and has a lower R naught. So there are several things that make it different. So, right, this is kind of the concluding bit. So those curves, those graphs we were looking at are super encouraging. They're kind of inspiring. On the other hand, they're only that way because we're all sitting at home. And so what happens when we stop doing that? No answers. I don't have any answers. I'm reading the same stuff that you are, just trying to talk about the quantitative aspects that make sense in a class like this. Okay, I'll ask you a few practice questions, and then we'll move on.